Hello, my name is Veeravalli, and I'm with the University of Illinois at Urbana-Champaign. I want to thank the organizers, particularly Yanis, for inviting me to participate in this interesting workshop. My talk will be about a statistical technique called quickest change detection and its potential application to predicting and monitoring pandemics. Let's get right to it. So what's the quickest change detection problem? So you have a sequence of observations, x1, x2, and so on. And the idea is that the distribution of these observations changes at some point, gamma, that's unknown to us. Okay, and so before the change, the distribution is some p0, and after the change, it is p1. And the change happens at some abrupt point, gamma. Okay, and the goal here is to stop at a certain point and stop taking observations and then declare that the change has happened at that point. So at some point, say tau. And you'd like for this tau to happen after the change occurs. Okay, but if it happens before, that means you've declared that change has happened before gamma, there will be a false alarm. And a good quickest change detection algorithm gives you a good trade-off between the detection delay and frequency of false alarms. There have been lots of applications of quick exchange detection, and this is a problem that's been studied for almost 100 years now. The initial applications were in manufacturing systems for quality control, but it's seen a number of applications, many different areas, in surveillance systems for intruder detection, in power systems for detecting things like line outages, more generally in infrastructure monitoring for detecting faults in systems, environmental monitoring, and also more recently in biological applications such as in detecting transitions from a normal to what's called a dysregulated state and monitoring neurological disorders. And there's a whole bunch more, which I'm not going to be able to list in the entire set of applications. But this talk is going to be about whether this method can be used for pandemic detection and monitoring. Okay, so again, the quick exchange detection problem is you're trying to detect a change in distribution from P0 to P1 that happens at some change point gamma. Okay, so let's look at an example, a computer-generated example of a sequence of observations that changed in distribution at some point. So in this case, actually, the observations go from um, Gaussian with zero mean and variance one to start with, and then it changes, that distribution changes at some point to Gaussian with zero mean and so a mean 0.1 and variance one. I, looking at this plot, you really can't tell. Such a subtle change in the distribution that you can't really tell by looking at the plot of the data. And one might guess maybe that it's around 500 because there's some large deviation here at 500. But it really, it could have been anywhere. It turns out that the actual change happened at 200. But again, one can't really, couldn't have said that from just looking at the sequence of observations. But then on the other hand, it turns out you can construct a test statistic on the sequence of observations with the following property. And this is called the Q-sum test statistic, and I'll describe this in some detail over the next couple of slides. And the idea is that this statistic stays small, takes small values before the change point at 200. And you'll notice that it hits zero a lot before it gets to the change point. And then after that, it starts to take off. Okay, and so it's showing a positive drift, an upward drift. And so eventually, you'll see that it can cross some large threshold, in this case, 4 in this example. And at that point, you say, okay, I think I'm pretty confident that change has happened now. Okay, and in this case, you declare that the changes happen with a delay of about 500. All right, so what is this Q-sum test? This was a test that was introduced by Page in the 1950s. And the idea is that you want to use the distributions of the observations in some way. So again, in this part of the talk, I'm going to assume that I know what the statistical characterization of the observations is before and after the change. And in this special case, let's assume that they are independent and identically distributed with some PDF or density F0 before the change and PDF F1 after the change. Okay, so an important quantity in such statistical decision-making problems when you're trying to test between distributions is the log likelihood ratio or the likelihood ratio between the observations, F1 divided by F0. Okay, and since we are getting these observations sequentially over time, the cumulative sum of these log likelihood ratio turns out to play an important role in these decision-making problems. Okay, it's just basically a sum of the log likelihoods from time one to time k. Okay, so let's see how that might be useful in detecting changes in distribution. So it turns out that if you look at this statistic, Sk, which is the sum of the log likelihoods, the cumulative sum of the log likelihoods, it has a negative drift before the change point. And you can actually see that the expected value of each component that contributes to this sum is less than or equal to 0. And this actually is a negative of a Kullback-Leibler divergence for those of you who are familiar with that kind of stuff. Okay, so it exhibits a negative drift, tends to go down before the change point. And after the change point, okay, this statistic will have a positive mean. The components have a positive mean. So this sequence will have a positive drift after the change point. So you can exploit the fact that the nature of the drift changes, the sign of the drift changes at the change point to construct a test statistic to detect the change. And that's the idea behind the Q-sum test. The idea is that you want to know when this minimum occurs, whether the minimum has occurred with some confidence in the past. So what do? You subtract out the current value of the minimum of this sequence S, okay, from the value at time k, and call that WK. So WK is the blue plot here, SK is the black plot here. And you'll see that, maybe I should use a laser pointer. Okay, so you'll see that this WK statistic hits 0 a lot. So it hits 0 whenever the value at time k hits the current minimum of the sequence of observations up to that point, of the sequence Sk at that point. Okay, and so in this case, for example, as it keeps going down, you'll see that WK keeps hitting 0 because I'm subtracting out the minimum, which is this point in this case. Okay, so this statistic is going to be small and hit 0 a lot before the change point because of this negative drift in Sk. But after the change point, it starts to take off and stay positive. Okay, and the difference of the level of WK to 0, okay, of this height basically, is also the difference of Sk to its minimum value. Okay, so if you look for a WK to cross some large positive threshold, then you can say with confidence that the change has occurred at some point in the past. That's the idea behind the Q-sum test. Right, so basically the Q-sum test uses this statistic WK, which is Sk minus the minimum of the SJs in the past. Okay, and the test is to compare that statistic WK to some threshold, large threshold D, and at that time you stop and say a change has happened. Okay, and a convenient thing about the Q-sum test statistic is that it can be computed recursively. So if you knew the Q-sum statistic at time k minus 1, you just have to add the log likelihood of the observations at time k and take the positive part of that. That's what this plus sign means, and that produces the statistic WK. So it has this nice recursion that helps implementation. So let's look at a typical evolution of the Q-sum statistic. So in this case, the change happened at some time gamma, which is equal to 60 in this case. And we'll see that if things are going well, your Q-sum statistic, okay, might go up a little bit, but basically hits zero a lot before the change point. And after the change point takes off and it crosses, say, some threshold 8 in this case, with some delay of about 20 samples. Okay, so this is a good situation, but you could also have occasionally a situation like this depicted in the green line here, where you cross the threshold of 8 uh, well before you get to 60. Okay, so that corresponds to a false alarm event, and the idea is that you want this test statistic to work in such a way that you get a good trade-off between these false alarms and delay. And I should mention that if I made this threshold large, then of course the delay would also go up, but then I might have fewer of these false alarm events, because this green line might end up going back down, hitting zero, and then I would not have to worry about not crossing the threshold. Okay, so so the Page introduced this test in 1954, and it was only about 25 years later that that someone decided to see if there was some optimality property to this test. It's intuitively, it seems like a reasonable thing to do, but is it optimal? And so Lorden was the first to propose a formulation. So he defined, again, this is getting a little mathematical, so if you want to skip over the slide, feel free to do so. But the idea is you want to measure delay in some manner, and he said that you should measure delay by looking at the difference between the stopping time and the change point. Take the positive part, and look at the worst case possible delay over all possible change points gamma, and all possible things that can happen before the change point, that the observations before the change point. And that's what this essential supreme is about. So this is kind of a measure of delay, okay, a worst case measure of delay uh, for any detection rule described by stopping time tau. And the false alarm rate is measured through the mean time to get to a false alarm in the pre-change regime. And the inverse of that is said to be the false alarm rate. So if we go back to this picture, basically, in this case, uh, the mean time that you have something like the green thing happen before the change point. Okay, and what happens is when you have a false alarm event, you'll probably detect that you would stop the system and look and check if everything is okay. And if things are okay, then you would restart the system until there's another false alarm possibly. And so you want to keep the rate at which those false alarms occur to be something small, so less than some alpha. Okay, and it turns out that this Q-sum test that I described 2 slides ago actually is optimal with respect to this criterion. Okay, and that's what was established about 15 years later by someone called Mr. Keys. And it was also shown to be optimal under various other criteria and models. And in fact, I've only talked about one criterion here and one specific model for the observations and so on. So there's the rich history on this problem. There are all kinds of other criteria that people have proposed for quick exchange detections, and also proposed many other tests that can be used for detecting these changes. But the Q-sum test turns out to be the most popular test among all of these tests. And in fact, if you do a search on Google Scholar for the term Q-sum, you'll find tens of thousands of references. So many applications of the Q-sum test And the typical criterion that's used is something like Lorden's criterion when you want to compare cross tests. Okay, so that's why I focused on those two in this talk here. Okay, so 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 again, one thing that's of interest in, in characterizing quick exchange detection algorithms is if is a performance analysis, or can you predict how well the test is going to do before you actually use it in practice? And there are two quantities of interest, of course, the false alarm rate and the delay. Okay, so you want your false alarm rate to be constrained by something. So you want to meet some false alarm constraints. So in order to do that, if you can analyze how the false alarm rate of a test behaves as a function of its parameters, in the case of the QSAM test, it's this threshold D, then you can use that to set the threshold to meet the false alarm constraint. And you can actually show quite easily for the QSUM test that the false alarm rate is bounded exponentially, like e to the minus the threshold. So you can actually set the threshold. If you set the threshold equal to log of alpha, then the false alarm rate is guaranteed to be less than or equal to alpha. And notice that this is not really a function even of the observation, the distribution of the observations. So that's another advantage of the QSUM algorithm. The delay as a function of delay can be also analyzed as a function of the false alarm rate. So if you set the false alarm rate to some level, you can show that the delay of the QSUM test actually goes as the log of the absolute log of that false alarm rate divided by the Kullback-Leibler divergence between the post and pre-change distributions, df1, f0. And so what this relationship tells us is that the false alarm rate actually goes to zero exponentially fast with the delay. So as I make my delay larger for the test, my false alarm rate goes to zero exponentially fast. And the error exponent is characterized by the Kullback-Leibler divergence between the distributions, which is an important distance measure in many statistical decision-making problems. Okay, so if you plot the delay versus the log of the false alarm rate, and that should really be WADD here, then you get a line you get a straight line whose slope, and this is actually a simulation with Gaussian observations, you get a straight line with slope that's 1 over df1, f0, verifying the analysis that I just described in the previous slide. Okay. All right. So what I've talked about so far assumed that I knew something about the distributions before and after the change. In particular, I assumed that they were IID before and after the change. But a lot of applications, including for the pandemic monitoring application we're going to talk about, that's not going to be the case. You're not going to know those distributions. So you might have some model for the distribution, say that it's Gaussian, but you may not know the parameters like the mean and the variance. Okay, so when there are unknown parameters in the observations of distribution, you need to do something a lot more sophisticated. And a lot of the recent work on quick exchange detection over the last 20, 30 years has focused on those kinds of problems. Okay, so three possible approaches one can take. One is the generalized likelihood approach, where you have a parametric model for the observations, and you maximize the statistic over the unknown parameters at each time step. You could have unknown parameters both in the pre and post change distribution. Okay, and under certain conditions, one can show that these kinds of generalized likelihood tests are asymptotically optimal. Asymptotics in this case typically means that we let the false alarm rate go to zero. Okay. Another approach is to hypothesize or postulate rather some kind of prior or weight for the unknown parameters, and then average the test statistic that you design over the distribution of those or using the weights for those unknown parameters. Okay, and that approach has also is actually, it turns out to be quite similar to the generalized likelihood approach in terms of performance, and there's been a line of work in that direction over the last few years. And a third approach is what's called the robust approach, where you try and identify what I call least favorable distributions for your decision making under the pre and post change modes. And then you design something like, say, the Q-sum test between the pre and between those worst case distributions. And under certain conditions, you guaranteed that designing it designing your test for those worst case least favorable distribution gives you what's called a minimax robust solution to the problem. Okay. Now, if you don't have even a parametric model, you can take a purely data-driven approach to the problem, and that's what people have been doing. Say that's more, more recently over the last 5 years or so, with the renewed interest in things like neural networks and deep learning. So, so you could take a non-parametric approach. Actually, I should say non-parametric approaches have been tried much longer than that. But the idea behind non-parametric approaches is to estimate things like the moment, some simple moments like the mean and variance of the observations, and then or histograms even, and then construct useful test statistics using these simple estimates. Okay, and I'll talk about using this approach specifically for the pandemic monitoring application in just a second. Other approaches that people have been trying recently is just a black box neural network or deep learning approach. So where you use the training data, because you're not going to have a lot of training data in the post change mode necessarily. But you may have a lot of training data in the pre change mode, and you somehow use the data that you have to build essentially it's a black box neural network that is able to detect when the distribution changes. And typically this is done by taking blocks of the observations and seeing if the block of observations at test time or at inference time matches the pre-change distribution data or the post-change distribution data. Okay, a more systematic approach was suggested by Mustakidis recently, and that is to try and learn the likelihood ratio using a neural network or using a deep neural network, and then use that learned likelihood ratio to build something like your QCD statistic that you would develop if you knew the distributions. Something maybe say a Q-sum type test. Okay, and so but of course, all of these assumes that you have some knowledge about post-change distribution as well. It's some data from the post-change distribution as well. And what I'm going to talk about next is what you only have if you only have labeled data corresponding to the pre-change mode. So what do you do then? So one thing we've looked at recently in my group is, changing the problem a little bit. So instead of saying I want to detect a change, any change in distribution of the observation, suppose I want to just detect a change in some moment of the distribution. Say if you want to detect a change in the mean. Okay, and let's assume that before the event happens, that causes things to change, the mean is constant and known, and or easily estimated. Okay, and after the event, the mean goes above some threshold. So the idea is you want to detect when the mean goes from something small, say, to something above a threshold eta. Okay, and it turns out you can pose this problem in a minimax robust setting, where the post-change distribution is characterized by an uncertainty set. So this a set of distributions characterizes what happens after the change, and that set is all the distributions for which the mean is constrained to be above this threshold eta. Okay, and we constructed an asymptotically optimal, a robust test for this problem, where we first assumed that you knew what the entire distribution before the change, and then after the change, all you know is that the mean is above eta. Okay, and so in that special setting, under that assumption, we could construct an asymptotically optimal test. But then we showed that this can be well approximated by a simple non-parametric test that only uses the mean and variance in the pre-change mode. Okay, and to convince you that this is a good test, we actually did some simulations to compare the performance of what we call the mean change test, MCT, and that's shown in red. This is the delay versus log of false alarm, like we saw before. And this will a reason why it's not quite a straight line here, because it turns out that the straight line approximation works well when this log FAR is a little bit larger. So initially, it's a bit of a nonlinearity here. So green line here corresponds to the Q-sum test that knows the distributions exactly before and after the change. Okay, and and I think the distributions in the simulation were beta distributions that were bounded between 0 and 1. And the red line corresponds to our mean change test that uses only the mean and variance of the data before the change point. Okay, and this yellow line or your green line here corresponds to the test that knows the entire distribution before the change point. And you see that these two almost perform identically to each other. So the mean change test is a very good approximation to the other test, the known pre-change test, which we showed was asymptotically optimal for detecting a change in change to a mean above the threshold eta. Okay, so we applied this test to see if we could pandemic data. So what we were looking at is the fractional of incremental cases in various counties in the U.S. Okay, and this is this data is available actually through the New York Times website actually, and so this is the fraction relative to the population in a county of the new cases that were reported on each day. So based on tests of the population. Okay, and so this was measured from I think this is number of days starting from Jan 21st, 2020. Okay, and so by day 150 or 160, this was when the first wave was nearly done, and things looked pretty okay for quite a while. Okay, so it's a long period where the number of cases wasn't going up very much, so just going up and down a little bit. So we can think of this as a pre-change mode corresponding to a wave of a pandemic. So the idea is that when you're done with the first wave and people start relaxing their social distancing and so on, and start opening things up, that you want to monitor the population to see if things are starting to get worse and maybe a second wave is starting. But what we thought of as an indication of a second wave might be that the mean infection rate, or mean number of incremental cases, goes above some threshold. Okay, and if it goes over the threshold, then that's indicative that we may be having a second wave. And the idea is that when people start socializing and so on, that the infection can spread exponentially. So there's going to be an abrupt change in the positivity rate that you see in the tests. Okay. And so we wanted to see if our mean change test would be effective in detecting such a abrupt change in the mean positivity rate. So we used our statistic, and you can see that that statistic. So let me tell you about how we designed the threshold first. So the threshold, we designed it to be about 3 times the pre-change mean. So we actually estimated the mean and variance using data from days 120 to 200, where things seemed flat in all these three counties here, for example. And we using this is so that's what's indicated in this blue line, and the green line. What we chose this green line, our eta threshold, to be about 3 times that. Okay. And with the understanding that if it exceeds the 3 times this, that's an indication, very rapidly. I mean, that's an indication that a second wave is happening. Okay, and you see that in all three cases, our statistic actually stays below. So this design threshold for the statistic was based on the value that we chose for the eta here, and the mean and the variance in the pre-change mode, which was estimated using data from 120 to 200. So this range here for all three. And you'll see that the statistic remains below that threshold, design threshold, uh, for, up until some point. So it's consistently below the threshold, even though this guy goes up and down. And then at the point where this thing is starting to take off, and well before it actually uh, crosses the green line in this case, you see that this thing is taking off vertically. Okay, so that's an indication that the um, second wave has started, and you'll see that in this, for example, in Hamilton County, Ohio, that second wave started long before the second wave started in St. Louis, for example. Okay, so again, decision makers in those counties could have used something like this to predict that a second wave is coming, and ask their citizens to be a little more careful uh, if if this mean change test was available to them. Okay. Now, of course, that's just one county, or you can think of counties or even zip codes to be points in a network, and neighboring counties are, say, joined by lines. And you can when you monitor a pandemic, it's maybe of interest to not just monitor whether a particular node has gone from uh, you know from a low infection rate to a high infection rate, or if a group of neighboring counties are all seeing seeing that phenomena happen, that might be a stronger indication that there's actually a second wave that's spreading really rapidly across the country. Okay, so one can actually use the statistic that we develop on a county by county basis, and we have ways to combine these statistics to detect when a subset of neighboring counties exceeds or simultaneously exceeds a certain infection rates. Okay, so that's another thing that can be done using these quick exchange detection procedures. And that might be, again, useful, especially if there's mobility between neighboring counties. You could control that to control the spread. Okay, so let me conclude. So what I tried to convey was that quick exchange detection can be used to detect. So quick exchange detection can be used to detect subtle changes in distribution. Um, we managed to construct a test that seems to be effective in detecting abrupt changes in mean infection rate, which might be indicative of a second wave of a pandemic. But the real question that we want to explore in this workshop is whether quick exchange detection can help detect the emergence of a pandemic. So before anything bad happens, so not just detecting second waves of the pandemic. So for this, we need to have a much better understanding of what indicators of such of a pandemic emergence are. Okay, and I took some of these terms from the description on the workshop website. So changes in pathogens, ecological interactions, and human behavior decisions can possibly be inputs to some mechanism that could potentially detect a change, an emergence of the pandemic. But the key question is, that's something I'd like to discuss with all of you, is do these indicators change stochastically when a pandemic is imminent? And that's important. So if it does, if these indicators do change stochastically, then getting some, some accurate observations of those indicators might be useful in constructing these quick exchange detection tests that can be maybe useful in predicting that a pandemic is imminent. Okay, thank you.